know what software-defined vehicle means really with a specific example? We get that question quite a lot recently. So we thought, let's explain, let's explore. Also, what might be differences to over-the-air? How does it really incorporate fleet management? What's the overall story? And that's why we have the one example today, an emergency brake assist feature we want to include into a vehicle after SOP. The scenario? Modern vehicles, they flash their hazard lights already. And new regulation comes in which says the horn also needs to be honked in such a case. So to warn others acoustically. That would be a medium to probably even a big catastrophe to bring in such a feature after the SOP. Because what you need to do is the brake ECU needs a change. The gateway ECU needs a change because the communication matrix is being updated. The horn ECU is being updated and potentially even the indicator ECU. Technically, this is all possible, but it's just too long, too many discussions, too costly. Therefore, such a change would not happen. And the question is, how can we do it better? How can we make it faster? How and what do we need to change? I'll show you. So in this video, what will you expect? We will have a look at the EE architecture. What do we need to do to prepare the vehicle? Afterwards, how do we get to an automated development and testing? How can we quickly change something? And that's where we do stuff live here as well. And last but not least, how can we update, collect data with connected solutions for a whole vehicle fleet? So let's dive right in and have a closer look at the continuous architecture and the software platform. What we can see here is the overall EE architecture. Of course, it's very simplified. That's our EE architecture in a system architecture view of our model car, which we will update later on as well. We have different ECUs ranging from very small, simple sensor and actuators through zonal ECUs, control ECUs up to really large and powerful high-performance computers. In the inner core, we have a dynamic setup. Here is where really this link, the trick of a centralizing architecture comes in, because we can dynamically connect new applications, new features. The outer area, the sensors and actuators, that's where things will stay and happen more in a static manner. That's why we have CAN-LIN communication there. How do we from Vector support? First of all, we provide advisory services for the EE architecture. But on the other hand, we also provide base software building blocks for all ECUs in your system. And that's where we will have a look at the software platform. Before I go into the technicalities, our core business is highlighted mainly in the red, purple and gray area. Your focus as our customer, that's really creating applications, creating value. The end consumer really has a tangible difference. The base software here is our microSAR stack, different products, different solutions which we can provide pre-integrated to you as a customer. On the one hand, the known products, classic and adaptive, for example, a lot of you might know. I'm not going into detail in this video. I'm going into the details. What is the new part? What are the new aspects? On the one hand, the challenge is connecting different ecosystems. For example, IVI, the infotainment system, the ADAS system with the vehicle world. That's a really high-performance computer, an HPC-specific domain. That is a link of our ecosystem gateway. On the other hand, we have new simple sensor and actuators because intelligence will be moving to the high-performance computer. For this, we provide a solution that enables commercial off-the-shelf and also a really lightweight solution. So it helps you providing them, and it also helps variant management. These can be completely the same across all of your vehicles. And the last aspect I would like to highlight is really the applications on the microprocessor area. What we provide is the so-called application framework. It enables you to have stable APIs, stable workflows on the application side. And that's a challenge right now because you need to have knowledge of the underlying technologies, and that's how we abstract it. And that's a core aspect of software-defined vehicles, having applications, your core business, as reusable as possible. But now let's have a look at how do we get from any change, how do we get from the result of our architecture to really doing stuff in a fast manner. So first, why is a software factory essential for software-defined vehicles? It's about being fast, and the main goal is accelerating the development, enable short release cycles, enable short feedback cycles. It's all about making the application developers happy. How? By offering granular software packages and a high degree of automation. Let's quickly reflect on the use case. We have our emergency brake assist. That's exactly what we want to do. We just want to change a few little things here and there, have automation afterwards, and potentially from there deploy to vehicle fleets if everything is working. In the end, we want to get fast feedback. If it's working, if it's not working, but that's the important part. If we look at our slide, we have on the left side the system architecture. Here we have defined our overall vehicle. That's what we have done previously, where we have a small architecture set up with several ECUs. What we want to realize is a decoupling with interface agreements. That means the application developer, they can work independently from each another. They can also work independently from the base software below. And that means they can develop, they can test in virtual setups already to get really a high degree of confidence. Is their code actually working or not? Because with a fast feedback, they can change it in minutes. The lower aspect, the base software, of course, has a lower cadence of changes. That also means here we also want to develop and test in virtual setups. We want to bring it together and then bring it to hardware, test first software in the loop and then hardware in the loop. The principle behind it is called shift-left testing, failing, succeeding as fast as possible. Another important aspect is the as-code paradigm, meaning I want to be able to change things in code or text-based, not in a UI-based manner. What's the rationale behind? It really helps with differentiating, with merging our code. It helps with version control. So all of the things we need for a good automation and a good infrastructure. And it also helps to use AI agents through the MCP protocol to access code to provide something a developer in the end only needs to review. Also here, speeding up the development process. How do we from Vector support? With first of all a powerful tool chain. It helps with development, it helps with integration, with testing, all the important aspects throughout the whole vehicle development. And on the other aspect, the even more critical thing is how do I change my organization? How does it affect my workflows? Where do I get blueprints? That's what we provide, proven workflows, also engineering services to get such a software factory up and running. How can we apply this in our real example? So what we have here is a standard software development infrastructure. The tools we are using here is exemplary. That's a GitLab pipeline. It's a GitLab IDE to change our code. What we have done here is we have prepared the emergency brake feature, the use case I've mentioned earlier. On top, what we can do is we can change the indicator in a fancy color. Which color would you choose? The change I'm doing here now in code is I'll change to the color of my choice and I save, and afterwards I hand in a commit reason. That means now I commit the changed code, push it to main, and now we can see here in the pipeline itself, now there is a new pipeline which has been created. When I click into this pipeline, we can see there are several steps which need to be performed. On the one hand, the generation of the HMI software cluster. That means now that the code is being centralized, features and applications are centralized, it's way easier to connect them to each another. That's why we also only need to really have a look at the software cluster on the high-performance computer. Once the generation step is done, we do a build of an ARM architecture. That means software built really for the hardware, and also we do a build for a virtual setup, so an x86 setup. When the build stages have been done, afterwards we test. First of all, SIL tests, software in the loop tests. Once they have been done, we go to a hardware in the loop test. And that is what we see here then also later directly in front of me. If everything is successful, we deploy, upload the new software package to our cloud. In the end, the use case here, the emergency brake feature, the application change, I as a developer want to really get as fast feedback as possible. We use the same configuration for the sill test and for the hill test, so the test code is the same. And now, probably in a few seconds or in half a minute, the hardware in the loop test will also run. That means sill test has been performed successfully, the hardware in the loop test checks is on hardware, everything also still the same. That means we will check the communication setup, we will check the functional features, and this might now interrupt me while I'm quickly explaining the setup here. So the setup is here the high performance computer in the middle, really the centralized applications, the center of innovation. It has connections through Ethernet to the zonal controllers, and the last part, the static aspect, CAN-LIN communication to the sensors and actuators. The application change only here, the sensors and actuators, they stay and remain static and just provide the access to the indicators and also to our horn as we have it on this board right here. And that's the same board. And now, while I'm talking, the hardware and the loop tests are being performed. We did see the indicators were flashing in our color, the horn was honking, and quickly one aspect, that's the same model we have seen earlier in our system architecture tool. We also run the tests here automatically against the whole requirements, and it's also the same board which we will see in our vehicle fleet. And now, let's have a quick look. The last part is still up and running, so it takes a few seconds more. Now it's successful. Our new software package has been released. We can deploy it, we can update our whole vehicle fleet, and that's exactly what we will do in our last part. What we will focus on now is the connected solution part. Vehicle-wide update management, vehicle-wide data collection. How can I deploy the software package I just created to the fleet? In our case, the vehicle fleet is one, but that's what we do. On the first hand, we have here our dashboard for the SDV cloud. That means everything I want to do from a connected aspect I can do. The part we will focus on is the software update management part. That means I create a new rollout. I choose the model to update. Here we have several models. This is the Vector Levetch. I save. I choose the latest software package, the one we just created. And the last part, I can choose now what kind of fleet, engineering, production, which region. I select the engineering fleet and save. Now I could configure way more things like Wi-Fi, 5G. I'm going to skip that. And now I need to do one additional step. I need to quickly log out and check from an approval perspective for ICE principle to approve the software package. And quickly log back. And now I can here click on Start Rollout. That means this will trigger the update on our vehicle fleet. As I said, it's a fleet of one vehicle here in this case. We have a polling mechanism of 30 seconds. So now our HPC is receiving the software package we have created in our development. And now I can simulate the emergency brake assist. How? By moving my hand quickly to the ultrasonic sensors. And if I do that, you can see and hear the indicators are flashing in the desired color, the horn is honking. So the use case we have described in the beginning, we have realized through several stations. On the one hand, the architecture, preparation of the vehicle. On the next step, the development and testing, automation, fast feedback cycles, and the application we have just changed and now deployed to our vehicle fleet. That is the overall development update process. One important aspect is, of course, now that I'm running and operating, how can I collect data? How can I improve my software quality? How can I generate new business? What we did is we have here on our dashboard an emergency brake assist event which we created. That means we can track all the emergency brake events. We have here a real vehicle, that's the one we have right here, and a virtual fleet. And what we can do is we can go into a specific one. The last incident here, we can track the ultrasonic sensors for the last 10 seconds, and the acceleration and velocity here, of course, 0 as it's a standing vehicle. This we can use for either creating new business or, as I said, maintaining, operating, and monitoring what is the overall software quality. Did something change which is not expected? And that's, in a nutshell, software-defined vehicle. Changes fast, safe, reliable, and secure, with an architecture which provides this, which enables this, with an infrastructure, with tooling, workflows, and processes. The demo we have done here to showcase this with our SDV cloud, with the connected solutions, and that's what we do from Vector. We know software-defined vehicles, and if you have any questions, or if you would like to get any kind of advice, how can you set it up? What's a good technology? What's a good framework? What might be a good solution? We're happy to get in touch with you.